data set as a physical landscape. To understand it, a machine learning algorithm acts like a magnifying lens. If you zoom too far out, details blur into useless noise. Zoom too close, and patterns beneath the glass warp out of focus. When we train a model, it discovers rules within the data on its own. We call these parameters. But engineers have to set the overarching constraints that govern that discovery process. These manual rules are the hyperparameters. The algorithm is at the mercy of these settings. Without precise human intervention, default configurations rarely bring the true data landscape into focus. The most significant dial an engineer can turn is model capacity. This setting controls how complex of a pattern the algorithm is allowed to memorize. This chart shows data points arranged in a distinct curve. When capacity is set too low, the model is too simple to recognize the shape. It draws a rigid, straight line through the center, missing the actual trend. We call this underfitting. If we push the capacity too high, for instance by letting a decision tree grow infinitely deep, the model becomes hyperflexible. It draws a jagged, chaotic line that touches every single dot on the graph. This is overfitting. The algorithm has perfectly memorized the random noise of this specific set, but it has learned nothing about the underlying pattern. When we introduce a new set of data, the model's predictions miss the mark entirely. This tension between bias and variance is the central challenge of the tuning process. Success depends on finding the sweet spot, where the model is flexible enough to see the curve, but disciplined enough to ignore the noise. Modern machine learning involves thousands of potential setting combinations. Testing every possible configuration manually is a task that quickly outpaces human effort. To automate this, engineers often use GridSearch, a brute force approach that exhaustively tests every joint configuration on a predefined matrix. This 3D grid represents the search space. GridSearch moves point by point, building a dense cube of results. However, this is computationally expensive. It spends a vast amount of processing time on variables that may not actually influence the model's performance. A more efficient alternative is random search. Instead of marching through every intersection, it maps the space using a scattered distribution of tests. Because it selects random coordinates, the algorithm explores a wider variety of settings for the most influential hyperparameters. When the data collapses into a 2D view, we can clearly see the clusters where the most effective settings are located. These search algorithms are the engines that turn the lens. But they are only effective if they have a clear surface to project onto, so we can measure the clarity of the resulting image. To maintain scientific integrity, we have to isolate the data we use for tuning from the data the machine uses to learn. This diagram shows our dataset. We slice off a 20% chunk, which is physically separated from the training pool by a protective barrier. This is the validation set. Our search algorithms use this held-out data to grade the model's accuracy after every hyperparameter tweak. The validation process acts as a compass, providing mathematical feedback on whether our adjustments are bringing the model closer to the target or further away. This firewall ensures the model is being tested against information it hasn't seen yet, forcing the algorithm to learn generalizable trends rather than just memorizing facts. But even this secure protocol has a vulnerability. If we run a search against the validation set too many times, we risk a new type of error. This is known as overtuning, or validation leakage. If we constantly adjust our dials to inflate the score on that specific validation slice, we are indirectly feeding the answers back into the training process. The model essentially memorizes the specific quirks of the validation set. It loses its ability to handle new information because it has become too specialized for the test. An overtuned model provides the illusion of perfect focus in the lab, only to produce inaccurate results when it encounters real-world data. To verify the model's integrity, we use one final threshold, the test set. This is a slice of data that has never influenced the parameters or the hyperparameters, providing the only true measure of how the model will perform in the wild. Building reliable AI isn't just about the volume of data, it's about the methodical, validated tuning of the lens that looks at it. But sometimes the optimal setting isn't on a dial at all. It's hidden within the very architecture of the network, a much deeper space that we are only beginning to map.